Good afternoon, everybody. Today we're going to find two derivatives using the definition of the derivative. So for the first one, we're going to have to use the binomial theorem. Hopefully that's something you've at least heard of before. I'll write down Pascal's triangle so we can quickly get the coefficients of the terms in the expansion. If you've never seen this before, it's simply ones in the diagonals, and then in the center, these numbers are the sum of the two numbers above in diagonal terms. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6, 1 plus 3 is 4, so on and so forth. And what they do is they provide us with the coefficients of the terms in the expansion of a binomial. This doesn't really, we call this the zeroth row. So first, second, third, fourth row gives us the coefficients of a binomial to the power of 4. And so since we're looking for the derivative, we are looking for f prime of x as the limit as h goes to 0 of f of x plus h, which for us means x plus h, that's not an h, x plus h, all to the power of 4, right? A binomial raised to the power of 4. That's why we need the binomial theorem, minus f of x, x to the 4, all over h. And so we're looking to evaluate the limit as h goes to 0 of, if we expand this, the two terms both have coefficients of 1. That's really convenient for us. So let's apply these coefficients to the terms. We know that the exponents on x, the first term, decrease by 1 with every successive term, and the exponents on h, the second term, increase by 1 with every successive term in the expansion of the binomial. And so that means we're going to get x to the power 4 plus 4x cubed times h, right? So this is like x to the power 4 times 1 times h to the power of 0, which is just x to the power of 4. Here we have the 4, we have x to the power of 3, h to the power of 1, right? And then we keep going. So the next term is going to have a coefficient of 6. 6, power of x goes down by 1, power of h goes up by 1, x squared, h squared, and then plus again 4, x to the power of 1, h cubed, and finally plus 1, x to the 0, h to the 4. And we still have, let's not forget that f of x minus x to the 4 all over their common denominator of h. And so we have the limit as h goes to 0 of each of these terms. Let me not forget to do something first. X to the power of 4 cancels out right at the front and end. And now every one of these terms has an h factor in it. So it's going to cancel out the h in the denominator. So this one goes away completely. This h squared becomes just h, this h cubed becomes h squared, and this h to the 4 becomes h cubed. And so now we're looking at the limit as h goes to 0 of these remaining terms. That's 4x cubed plus 6x squared h plus 4x h squared plus h cubed. And now finally, since we have no more denominator, we can apply this limit as h goes to 0 by plugging in the value of 0 in for h. And since h is going to 0, all the terms that have an h in it go to 0 as well. And so all that we are left with for the derivative f prime of x is 4x cubed. And of course, you can check that by using the power rule if that's something you've learned already. And of course, it works out perfectly. Okay, so that's our first one. The second one, we're going to use the definition of the derivative for this rational function, right? We'll have to use a bit of algebraic manipulations to kind of get those denominators to work out. And so if we want our derivative function, g prime of x, using the definition of the derivative, we're looking at the limit as h goes to 0 of f of x, rather g of x plus h, right? So g of x plus h is going to mean 1 over x plus h minus g of x, that's 1 over x, and all of that over the denominator of h. So let's go ahead and manipulate that as needed. We are still evaluating the limit as h goes to 0 of, let's get a common denominator in that numerator. So let's get both over x times x plus h. So we'll multiply the first term times x over x, this term times x plus h over x plus h. And so that brings us to the limit as h goes to 0 of x minus x plus h all over x times x plus h all over h, which is the limit as h goes to 0 of x minus let's be careful here, x minus all of that second term, right? Minus x plus h. So x minus x is, of course, 0, cancels out. And so we get negative h all over x times x plus h all over h. And now those h on top and on bottom cancel out. And so we have the limit as h goes to 0 of negative 1, right? Negative still there, over x times x plus h. And now plugging in the value of 0 in for h doesn't create any problems. And so we can evaluate this limit as h goes to 0 by making h take on the value of 0. And what that leaves us with is negative 1 over x times x plus 0, which is x squared. And so our derivative function g prime of x is negative 1 over x squared. We can check that really quick using the power rule, right? G of x, box this off, is 1 over x is the same thing as x to the negative 1. And so that means that its derivative is multiply the exponent out front, drop the exponent down by 1, so that's negative 1 x to the negative 2. And as you know, that is the same thing as negative 1 over x squared, which is what we got using the definition. And so really hope this helps. One word of advice, just don't forget about minus f of x. That's such an easy little mistake to make. Be mindful with your brackets, with your negatives, and then only evaluate the limit when h goes to 0 at the very, very end, when there are no more problems to deal with by plugging in the value of 0 in for h. So really hope this helps. And as always, thanks for watching.